a little sketch of the wind to start with before I talk in a bit more detail about its characteristics. So this is a sketch, as you can see, of the wind blowing over or from the left, a sort of forested or rural area, coming to a industrialized or built-up area. The red lines at different heights are the speeds. So the longer the line, the higher the wind speed. And you can see as you come down towards the ground, the wind speed reduces, and we call that a boundary layer. And as you go up, actually very, very high, in this case 2 kilometers, you get to what we call the gradient height or the gradient wind, which is pretty much constant. And you can see also in rather a simpler way, we've got a sort of wiggly line defining the boundary layer. And that's intended to show that as you get closer to the ground, the wind becomes turbulent. And you will have experienced this if you've been up in an aeroplane. As you take off or land, the flight is quite bumpy, but when you're cruising, it's pretty smooth. And when it's bumpy, you're in the boundary layer. So the aeroplane has the benefit of getting out of the boundary layer and cruising along in smooth wind. The turbine lives its life in the turbulence of the boundary layer. So the characteristics of that boundary layer, or the wind in the boundary layer, are rather important. But here we are showing the wind speed varies with height. And so if you have a taller wind turbine, you get more energy. And that's an important part of the economics and the design driver for turbines. Until the last, let's say, decade, pretty much every wind measurement that was made, wind speed measurement that was made using an anemometer, which looks like this. And I'm sure you've all seen this sort of instrument. And it will be mounted on a mast. And here I think is a 40-meter mast, which in the days when the turbine hub heights were 40 meters was a sensible level to use. Now, well, even 100 meters is probably not tall enough, even just to get to the hub height. But anyway, we have continued to use these instruments and continued to get taller and taller masts. And they are used to make point measurements. In this case, we've got 1, 2, 3, 4 points up the mast in order to try and get an idea of the profile of the boundary layer that I've just shown you. Well, that was the old days, and that's much perhaps easier to understand than now. We have 2 different remote sensors which are often used. One is called LiDAR, the other is called SODAR. They were level pegging, but pretty much now the remote sensing is done by LiDAR, which is lasers, SODAR is sound. You put this device on the ground, point it upwards, and it will measure wind speed above it directly. And you can see from the early days when I was showing you the profile of the boundary layer, and bearing in mind the height of the masts we used to use and the height of the turbines now being adopted, this remote sensing is pretty powerful stuff. Quite expensive.
So does it show you the wind speed at different heights above the laser?
Yes, it's incredibly clever, really. There are some disadvantages. It's actually, well, I don't know if they're disadvantages or not. Well, a quite interesting thing about a little anemometer, you're using this little anemometer, probably about 6 inches across, to give you an idea of the wind speed coming into a turbine which might be 150 meters in diameter. So that's a pretty weird thing to do. So you would like to have lots of anemometers. What this does, the LiDAR, is it measures the wind speed over rather a bigger volume, so bigger than the anemometer. But in a way, that's a good thing because you're trying to use it on something which is bigger. So this has been a major change in methodology. But so something will be used to measure the wind speed. Might be LiDAR, might be SODAR, might be a good old-fashioned anemometer. Now, this is slightly more adventurous, but last year in 2019, the 𝐦𝐬𝐿𝐴 satellite was launched. The 𝐦𝐬𝐿AS satellite sole purpose is to look at global wind speeds. So it's there to measure wind speed. It's perhaps not so interested generally in what's going on in the first 100 meters where we are. Very interested in looking at bigger patterns, but it's being used for that. So this is another major bit of armory that we've got to attack the wind. So typically, if you're developing a wind farm, you will start with a short-term measurement. Short-term, I don't mean a few minutes. I mean a year or two. But short-term measurement on a site. Then, that's quite nice to have. But of course, what you really want to know is, well, what's the wind like on that site generally? What's the long-term behavior of the wind speed? So what you'd love to do, of course, would be to make the measurement on the site with your mast for 20 years. 20 years later, build the wind farm. Well, okay, you might do that, but other people might overtake you on the way. So somehow we have to shortcut that process. So typically you're making measurements on a site for a year or 2 years. And then we have to use that short-term measurement, that little window into the data, to get an estimate of the long term. And the way we do that, if we're lucky, is to be able to compare the local wind speed measurements on the wind farm, as it says in this diagram, with some distant, well, may not be distant, but some reference station. That reference station doesn't have to be very close, but it has to be similarly exposed. So if you are in a very flat terrain with nothing much in the way of mountains or hills in the way, it could be 100 kilometers away, and you would still find that the prevailing wind behavior was similar. On the other hand, you could find that there was a great big mountain in the way, and you were only 10 kilometers apart, and the wind was completely different. So you have to use your head a bit to look for these reference stations. But if there is a reference station, and it's a reliable reference station, then it's very useful. So you're looking for a consistent long-term set of data. And assuming you found it, you go there, you must go there and have a look. Then you compare the data on your site with the data on the reference station. And gradually you build up a pattern. You hope. Maybe you don't. Maybe there isn't a correlation. And interestingly, the absolute accuracy of the reference station doesn't really matter. So provided it's unchanged, it's consistent, the absolute accuracy is found from the anemometer on your wind farm. So you're making very accurate measurements of the wind speed on the wind farm, and you're just correlating with something consistent. So if the distant one is always wrong by a factor of 2, provided it's always wrong by a factor of 2, it doesn't matter. And we used to find that it was very important to go and visit these stations, because there would be written records of what they were doing and how they behaved, but often they would not be complete. And by going there, you could talk to someone, and often, maybe there's an interesting psychological aspect to this, often people making wind measurements have been doing it for a very long time. It's a characteristic of the sort of people who want to make a wind measurement. So they would say, oh yeah, well, we didn't write it down, but of course, 5 years ago, that hangar was built, or the farmer cut down that forest or whatever it was. And just as a little bit of an anecdote, on one occasion, we were doing a wind farm in Greece, on a Greek island. And so we followed our protocol, which is to go and visit the reference station. And one of our engineers went to the reference station, and the reference station was being reported by the local priest. And so he knocked on the door of the priest and said, oh, good afternoon, I've come to look at the reference station, the anemometry station. And the priest said, oh, well, I don't know what you mean. He said, well, you've been reporting the wind speed on this island for the last 20 years. Oh, yes, that's right. So where's can I see the anemometry? Oh, there isn't any anemometry. He said, oh, sorry, I don't understand what's going on. Oh, well, what happens is that every morning when I leave my house and go to Mass, I look at the sea and I report how high the waves are. Which, on the face of it, sounds okay, useless. But actually, same guy, same time, every morning for 20 years has been making a consistent observation. So that's probably the extreme end of consistency. but it also tells you that you do need to go and look. And that process, so measure on your site, correlate with a reference station, and then predict the long-term wind speed on your site is called measure, correlate, predict, or often referred to as MCP. Now, if you can do that, if that data is available, then it's very useful. That data is only available in places where there is quite a sophisticated meteorological service, and often is not available. But if it is available, you should use it, but be very careful. And here's some examples of the correlation process. So the x-axis here is the site mast, so the short-term measurement. The y-axis is the reference mast. And this is for different wind directions, and you can imagine that the correlation might be different from wind directions, particularly if there's a mountain in the way or something's going on. In fact, these all look very similar, and I've said here this is a good wind speed correlation, and it obviously is. I mean, you can, at a glance, you can see, well, those two parameters are clearly related one to another, so that's good news. You can do the same thing with the direction. This is reference mast direction, wind direction, and the site wind direction. Again, pretty much they come from the same direction. It doesn't matter a great deal if that isn't a straight line, provided there is a correlation, a clear pattern. So those are examples of good correlation. Then similar thing, but for obviously rather less well correlated wind speed measurements. So now we're getting a bit into uncertainty. So you can see from this, yes, there is an underlying pattern. It does seem to be generally more windy on the site when it's more windy on the reference site, but there is quite a big spread here. So there's much more uncertainty attached to this estimate.
So what do you do in the situation where the data doesn't correlate?
Well, in this, you have to decide. In fact, it's dangerous because you've got a reference site. It's always often quite tempting to use it simply because it's there. But what you actually have to do is to look and see, well, if I use this, how big is my uncertainty going to be? Maybe I'm better not using that. Maybe I'm better just using the site, the data I got on the site, and making the best of that. So there is a bit of a grey area in here where you have to make that decision. So the mast location is the starting point. So we've got a mast on our site, and we're doing our very best to estimate what the wind speed is at that mast, and derive the long-term wind regime wherever we've got one of those masts. But we actually need the wind regime all over the site. So you're not going to make, well, it would be lovely to make wind measurements, put up a mast or a LiDAR in every single location when you're going to put a turbine, but that's financially impossible. So you wouldn't do that. So you need to make an estimate of how the wind speed varies over the site. There are various ways in which you can compute, or well, at least you hope you can compute these effects. So this little map here, the brown map, is a simple contour map of the terrain, and the black lines are elevation. And that white dot is where we've put up a mast. And so a terrain map. We can then turn that into a wind speed map using a computational tool. So the right-hand side, the yellow one, is now exactly the same terrain. You can see the mast is marked. But now the contours are wind speed contours. And if you look very closely, you can see where I've got the white dot, the contour is 1. In other words, it's the mast. And everything else is normalized against the mast. So you can see, I think, that this is pretty important stuff, because we've got a good knowledge of the wind speed at that white dot, but we're going to put the wind farm all over this hill. So we need to know how the wind is behaving in all these different places. And actually, this is shown averaged over all the directions, but it will be different for different directions. So if the wind is coming from one direction, it'll speed up, another direction it might slow down. So this is often done by tools called computational fluid dynamics, which is using a computer to look at the fluid flow, usually abbreviated to CFD. It's quite dangerous stuff, this, because CFD produces the most beautiful colored maps.
Hey there, thanks for watching. This clip was taken from the Certified Project Finance Analyst program. CPFA is a transformational 8-week experience that fully simulates a real-life project finance bid from start to finish. It will help you gain years of project finance experience from active industry professionals. You can find out more about the program by following this link.